All right, so thanks for being here. As I said, we're gonna just when you are when you feel moved, come up and share what you worked on. It doesn't have to be like here's my awesome demo of like a million lines of code that you wrote today. Mohammed and I are gonna start. You will see that the bar is very low as far as
Thanks, man. Are there emojis this year?
Well, there were emojis last year, which was amazing, and the emoji project was one of the hackathon winners. So we do have some prizes. Is this the prizes? I hope these are the prizes because they're up here. I'm going to give them out. So think about which is your favorite hackathon project as you are seeing them, and we're going to have a Google form that you can vote on. And the prizes are Bluetooth speakers and a wireless charging pad for your phone. And there's a bunch of each of them. Whoever gets first place gets to pick, and then we'll keep going down the list. Okay, any questions about logistics? Hopefully we will not be here past 5 o'clock. All right, we'll start. So we looked at performance of these dual actuator drives that Mohammed talked about. And the really interesting thing that we found is, so here's, we found that the performance for random reads was not what we expected. It was not nearly twice what it would be with 3 disks. So with normal disks. So here we have a pool. It's called Simple. It has 6 regular 1 actuator, old school disks that we're all familiar with. We ran FIO to create a bunch of files and then do random reads on them. The interesting thing that you may notice is that this is how much space is allocated from each drive. It's all 5 gigabytes. Everybody cool? All right. Everything makes sense.
Evenly divided.
Evenly divided. Space is evenly divided among the disks. Here, we did the same thing on a dual actuator. So this is 6 buns coming from 3 different actual physical disks. And you'll notice that, so SD, G, and H are 1 physical disk, and then I and J are 1, and then K and L are 1. And you'll notice that the first one of each of those pairs has a lot more space allocated from it than the next one. So when we did the FIO random reads, we saw that, these 3 were all getting hammered really hard, and the other 3 were not, which makes sense because they don't have as much of the data on them. And we realized that the reason this is probably happening is that as part of the work that we did a while back, ZFS tries, when it's doing writes, it's trying to allocate space from the fastest disks. So it's just giving a bunch of IOs to all the disks, and then as they complete, it gives more IO to them. So it's like, whoever runs the fastest, we make them run even further. Because we want everyone to be running all the time, by which I mean we want all the disks to be doing writes all the time when we're trying to do writes. And so it looks like, basically, in these 2 LUNs that come from 1 physical disk, one of them appears to be faster than the other to the operating system. We don't know exactly why that is.
Yeah, so I'm pretty sure I'm going to go back to the firmware guys, and they're going to be like, "Oh, your old firmware, upgrade to the latest one." And I've already been asking them these questions because I was emailing Matt back and forth, and we were having some performance issues. And every time I asked them, they would just upgrade to the latest. And since these are test units, I had to actually get a newer one. I can't just upgrade the firmware. So I will actually inform the community once I'm to the latest and greatest and figure out if it is a firmware issue, if it's a coupling issue mechanically with the actuators, or what's going on. So hopefully I can update everybody.
Would that be posted in the Slack channel? Where would we find that?
I can, yes, Slack channel will be fine.
Or the mailing list.
Mailing list?
Yeah.
You don't want mailing list.
This is a great place for that.
That looks like consistently zeros.
Yeah. Yeah, so it seems like there's some kind of bias where that one performs better.
Yeah. So that's the random writes doing that, right?
Yeah, well, random it's more like sort of sequential. It's probably more or less sequential, but small rates. Yeah. Cool. Thank you. So whoever is next, please come up, and this is your adapter, right? Do you need an adapter? I think I have one here. That's not the right one.
Oh.
USB-C adapter. Yeah, Thunderbolt or whatever. No, upside down. Oops.
Oh, and one other point. Before you start your presentation, can you please say your name so that I can write it down in this spreadsheet that we're going to vote on? I know your name, Don, but I'd like everybody to give me your name because some
My name
people's
is Don
names I don't
Brady
know.
from Delphix, and I was inspired by Paul's talk and a little bit by Brian's talk. And it's always when you understand these subsystems, you always kind of want to drill deeper and deeper. So he was talking about fragmentation, and we've been doing mitigation attempts, and we've had a couple efforts to try to create fragmented pools so that we can run our algorithms, run performance tests, and see how we adapt to fragmented pools. And they all involve a big N for time because you have to go write a bunch of stuff. So I had this idea yesterday, well, what if you just write an allocator that's just really crappy, and then you just over time just make fragmented pools. So that was my hack. So to do that hack, I had to understand how does the allocator work? You get this giant, you get a Metaslab with a giant thing, and then what does it do? It's it peels off a piece, and it's so I observed what it was doing. That's always the first step, and then I try to figure out what this fragmentation score is. How can I make a worse score? So that was sort of my hack, and I'll show you. So I was just using Z-test. It's not the best, but it's quick to do iterations on. So you typically see something like this where you have a whole bunch of smaller buckets, and then you have these bigger buckets. So my first attempt was just, hey, let's always divide it in half every time we do an allocation. And so we start making it smaller. So you can sort of see, so on that first point, it's I actually am printing out the range tree every time I'm going through there. So on just one of the Metaslabs, so I can sort of see how it progresses over time. And so I could see my efforts of dividing and conquering are actually working pretty good. So when you get down to, what is it? ZDB. So in ZDB, you can actually dump out the buckets. And so you can see, what's going on. So I can see hey, I got some good fragmentation on the big end, which is what I was doing. And I'm currently working on doing holes. So for the smaller allocations, try to skip around so that I generate lots of buckets there as well. So that's my hack. I think it'll be useful to generate pools that are really fragmented. So then we can make the defrag or other optimizations that we want to do later.
Of course, I need the other adapter this time. Hi, my name's Ash. I'm with Panzura. And for my hack, I took one of Alan's low-hanging fruit items from the spreadsheet from, I guess it was last year maybe. He wanted to improve the user experience. So we're going to do a little skit here. I'm going to be a hapless sysadmin about to make a mess with my Z-pool. So I'm going to start. Not an eye test. Everyone can see this. You can watch me type on my computer now. Okay. I am going to do something that I probably shouldn't do. And I'm going to add a singleton to my mirror. So we're going to stick DA2 on. Oh, well, we can't do that. But I am an extremely impatient sysadmin, so I'm just going to add that -f.
It says to do it right there. Yeah.
I know, and here we go. Here's the hack. Add -f now requires an override for check replication or check device in use to force a VDEV into a thing that it's not supposed to be in. Okay, you know what? I'm really impatient, so I'm going to typo that to go ahead and be a member of the pool, and I'm going to say we're going to force the check replication. Aha! Okay, this is also invalid because DA0 is now part of an active pool, so we caught that separately. So we have separate Mollyguard switches for everything that can go wrong. Not everything, but a lot of the common cases where people destroy their pools on day-to-day ideas. So this sysadmin is truly hapless and truly frustrated. Now he's going to do the wrong thing. Now he's going to check. In use. So nothing can help him at this point, but we've caused him to do 3 minutes of extra typing. There's a gotcha here, and Powell went over this, that, well, this is not precisely Pola and sort of isn't backwards compatible because we're changing the way, we're forcing -f to take an argument now. So I welcome discussion about how to turn this into something that's correctly bubble wrapped.
Dash capital F.
Or Fs.
More Fs. BBBF. All right.
Thanks, Ash. Who is next?
Hello, I'm Michael Dexter, and this is Karen Ritter of Delphix. And we worked on the wiki/OpenZFS main page because it's been until about now like, hello from 2013. And we might have new platforms, we might merge some new code bases, and we might kind of join the future. So with so much going on, we have put out the most pressing fires. We have removed a few bankrupt companies and merged and purchased and all the things that happen in this industry so quickly. Thank you so much on all of that. And it's time for, say, new content. Or, wow, do we still keep it with a wiki? We don't know. It is running. It will need a new home at some point, but we have some ideas for that. That's the easy part. But your participation is very welcome. If you're at a company, virtually all of you, please take a look at it and see if the company's list has you represented. It has you represented accurately, and all the things for just sort of portraying the modern OpenZFS that is represented by this event as opposed to 2013. So in other new content territory, I've learned that both Delphix and Brian's team are using the performance test suite in the ZFS on Linux repo. Great, just there it is. It calls FIO with a script. It does a bunch of things. Hooray, we just heard from Don about the built-in Z-test, etc. I would very much like to have a page on making that easy on the wiki, because when wonderful people like Mohammed join the group and they're like, I would like to just aim your file system at my new hardware, there are countless blog posts with random FIO stuff from people, just like whatever. And then suddenly it's like, well, none of us can produce the same answers on anything, and that's enough challenge alone on ZFS with any given software. So if you are at a modeling your workload with, say, FIO, saying, oh, we're a backup vendor and we represent all these Windows machines by this FIO profile, or our database looks like this, let me know, because I think it'd be great to have the Delphix test, or you name it, whatever company, and just having us on the same page is probably a good thing. Any comments for you?
As Michael said, there's a bunch of really out-of-date content like the FAQs and developer resources and documentation. So if anyone wants to contribute to that, please let us know. On Slack or otherwise.
Thank you. Thank you.
I was saying, I think there's another one.
We'll see if I can do this.
Go Linux.
Yeah.
Yay.
All right. Well, that's large. But what I worked on is expanding SDB to have a B-tree walker. Yeah. So we can use this kind of lengthy command to find a populated B tree. It's the MS allocatable one, and we can see, oh, it has 721 elements. The height is only 1 and only has 3 nodes, so it's only like a node with 2 things going down. But so it's pretty simple. But I can walk it and cast it to a range tree, and we can see these ranges are increasing, which is good. And I can also count the objects, and we can see that, yeah, we end up with the 700. It changes like pretty quickly, but 700 entries, and you can see I kind of printed out like the strategy for traversal. Like we start at the top, we visit a core node, we look at one entry, we see here at sub entries, go back up, see kind of the recursive descent. So seems to be working super well. The big part of this was just learning how to develop for SDB, and it was pretty simple. So would recommend.
Hi, my name is Rohan Puri, and I have sent a pull request, which is a bug that is in range tree implementation, so which is recently got merged. So I've sent a pull request for that, and also I took Brian's FiMap implementation. I've rebased it to latest master, and all the test cases that he has written, it is passing. So yeah, so I've sent a pull request for that as well. The pending part in that is review comments are still needed to be addressed. So I'll be doing that after later on. So, yeah, that's all from us. Thanks.
Okay, so I looked into resumable send and receive and how you can protect yourself from forged resume tokens, because as you all know, like you just copy paste the resume token from the receiving side to the sending side to resume your send. But if you're like developing a solution to replicate file systems between hosts that do not necessarily trust each other, you might want to protect yourself against arbitrarily forged resume tokens. And to do that, I implemented a fake or forged token generator. It's basically a lot of copy-pasted code from the DMU code that generates the resume tokens. And you can see here that we are generating a resume token that sends from a data set that we, as the sending side, don't actually want to be sent to the receiving side. So this resume token will tell the sending side to send the snapshot P1 secret at A with this GeoID from the beginning, like a normal full send. So we can look into that, or we can start to generate that token by running the fake token command. We'll spit that token out and copy paste that to the command line. And we can actually see that this ZFS send command would send, like it would perform the full send of the secret data set, despite us actually wanting to send the public data set at A. So let's try what happens when we do the send. It actually worked. So we have sent with the forged resume token, and we can see that we extracted the secret. So not good. And the solution is that you re-specify all the arguments that you want to make sure ZFS send actually uses, again on the command line together with the resume token. So in our case, when we expect that the resume token will send the public at A snapshot, we'll specify P1 public at A. And now, if we receive that into another data set, then ZFS send will complain and tell us that the to name in the resume token and what's specified on the command line does not match. That's it.
My name is Alec, and I have an update on the talk I did yesterday. So after a minute conversation with Tom, we were able to figure out what was wrong with the re-encrypting part of the healing receive. So apparently if you try to do ZIO rewrite for a encrypted block, it ends up trying to re-encrypt it again, which we don't need because we encrypted it already since we need to figure out what the checksum was. Yeah, so solution is simple, just make it a raw rewrite and it all works. So I updated the pull request and hopefully some of you will go and review it at some point.
Actually, don't know how to do that, so I'll just leave it as is. All right, so I was kind of in a mad scientist mood, and I wanted to see how hard it would be to compile ZFS to one ZFS.ko file with no other modules, so no SPL.ko, no ICP.ko. And as I started working on this, I was talking to Don, and he's like, well, you can't really do that because SPL is GPL and everything else is CDDL. So first thing I had to do was make SPL CDDL. And to do that, I needed to make sure that the SPL didn't call any GPL functions. So that was a lot easier than I imagined. So if you look in SPL, oh, that doesn't help. Well, anyway, there was only one function that was GPL that we were calling in SPL.ko. And so it was like an HR timer wait function. So I changed that to a different function and it built. So then I did some unspeakable things to the module makefile, which gave me this ZFS.ko, which is 118 megabytes. So if we do a mod info on that, you can, well, you might not be able to see, but you can see all the module parameters are in there. The problem is when you load this, it panics. And it seems to be panicking, adding a procfs entry. So that's it. Thank you. How does this even work?
Hi, I'm Jordan. So we worked on, while we get the laptop set up, a mutex SDB command. So I worked on it with a VM that didn't have ZFS, just to see if I could print like the folder of a mutex and the waiters. But then it was hard to find a mutex that had that was held or had waiters. And so Seraphim tried it on his system with ZFS.
Yeah. So I thought, what's cool? What's something that you want to look at ZFS? And well, let's say you have a crash or some kind of deadlock, right? And someone's holding the span namespace log. Actually, I had a crash that someone had done something similar. It wasn't a deadlock, but what I want to show off here is you can print who is holding the span namespace log, and you can also print anyone waiting on the namespace log. And you know what's cool about it is like, okay, this is not as efficient as I'd want it to be, but you can see, okay, this thread is definitely waiting on the mutex log right here. And if you want to look specifically for the one holding the log, is this one, and this one is waiting on a CV wait, and then you can go from there, depending on other things. But and that would be it.
That's it.
I'm Brian Atkinson. I'm from Lanel.
I'm a lot fallen.
And so we were working on a D-Array rebase, and we got pretty close. Just some things were breaking with the range tree stuff.
Yeah, basically it applied fairly cleanly after a little fussing around, but Metaslab changes made it not work. So we got to rewrite one bits of code to account for that. And then we'll see what fusses.
Hi, my name is Ravi Bachu and I work for Nutanix. So yesterday when you mentioned that ZFS is now moving to just, not just ZFS on Linux, but OpenZFS will also have ZFS on FreeBSD, it made me start thinking about one of the features which we built in Nutanix, but it's not out there yet and it's not been merged, but it's there in our private repository. I call it directory level snapshot access. So what I was wondering was how I would actually merge it into FreeBSD. And so as part of this hackathon, I started thinking about what challenges there might be and try to come up with solutions for that. So it's mostly in this part, I first describe what this feature does, and then I will talk about how to handle the challenges. So it's actually quite simple. It's just like the dot snapshot at the root today, but except that there is a directory called dot snapshot in every directory in the namespace. So people can browse into it and then see the different snapshots in which the directory was present, and then see the version of the directory at the time the snapshot was taken. So I have actually, this is an example of that. So for instance, if you had this directory called /foobar in your data set, this one, then and you had snapshots S1 and S2, then you can actually go into dot snapshot in the bar directory and then go into S1 as well as S2 and see the old version of the directory bar. So this helps people in restoring their old versions of files if they lost something or something of that sort. And this kind of feature is there in other NAS products from EMC and NetApp. So we felt that this would be useful, and so we built it and shipped it maybe about a year back. So it's in production right now. Some of the other aspects of this feature is that we don't list dot snapshot because tools like find and all might actually traverse down the directory. We try to preserve the same path through which there can be multiple paths to enter a particular directory. So for instance, in this case, you could have entered the old version of bar by going to dot snapshot at this level or dot snapshot at that level. So we want to preserve the same, the intent of the feature is to preserve the same path, so somebody could cd in and then change into the directory and then come back up into the parent and still see the same paths. And we try to also support existing file systems. It's not just for new file systems that are created. So that's kind of what the feature looks like, and I'll next proceed to how it is. Give a brief overview of how the feature is supported on Linux in our private version. So we don't actually have this namespace on disk. We create pseudo inodes, and as you might know, the inodes have these inode operations for listing and doing lookups. So we just need to support those operations for implementing this feature. And the users are pretty much oblivious of how we stitch this namespace. We use mounts and unmounts dynamically. So the typical user doesn't need to actually do any mount or unmount, and so that we don't have lots of mount points. Mounts also expire with time. That's kind of like the dot snapshot at the root, which we currently have in ZFS. This feature depends on certain Linux specific aspects, and that's where the challenge or any problem could be importing it to FreeBSD. So the first aspect of Linux which we support, which we depend on, is something called bind mount, which actually takes any particular part of a namespace and mounts it at a new point. So it can be invoked by using the -- bind option in the mount command. Now something like this wouldn't be there in FreeBSD, so this could be one challenge. Then another one is where for these new inodes, which we like the dot snapshot and the dot snapshot /snap name kind of inodes, we need to come up with unique inode numbers, and we do this on ZFS on Linux by just leveraging the fact that ZFS is only using 48 bits in the Linux version. So we use the other 16 bits to stuff in some bits to come up with new inode numbers. Plus, VFS has its own, Linux VFS has entries, which BSD VFS doesn't. So, as part of that, it has a d_automount callback, which we provide an implementation for, and we use that implementation to mount when somebody does a lookup. So these are kind of some of the Linux specific aspects. So in the case of FreeBSD, we could. So this slide is basically about how we could handle these challenges, and that's what I listed down here. So in the case of FreeBSD, we don't have bind mounts, but we could easily call into the VFS mount functionality to do that. In fact, that would be ideally what we should be doing, but in Linux, it's not possible because of the licensing aspect. This functionality cannot be utilized by ZFS, which is there inside VFS. So what we do is that we actually call into user space and invoke the mount, the bind option. Again, FreeBSD differs in the sense that it uses all 64 bits. Thanks to Alan for letting me know about this today afternoon. And we could probably follow the same approach, given that 2.48 is a big number and we may not create any directories with that inode number. Another approach we could do is to actually allocate an on-disk inode so that that same inode number is not utilized by the file system. And again, we don't have the mount callback. We don't have the DM scope. This should have been auto mount. There's a typo there. So we don't have the callback, but we could easily hook onto the lookup routine which ZFS provides to. So that's all I have. Thanks.
Yeah, it's Ajay from Nutanix. We'll just go over what we did to make L2R faster with NVMe drives. So just a note on the NVMe SSD that we used. Theoretically, it can do up to 1 million IOPS. So just know, I think we'll skip the overview part. So we just threw in this pool with one NVMe drive as the L2R. All that we could do is 100 IOPS. So that's where it saturates, right? So why is it so? So what we found is the CFS is very inefficient in terms of handling reads and writes, the CEO pipeline and the threading model. Right? We incur at least 4 context switch before the IO comes back to the user thread. So that's essentially depicted here, right? You have an application thread which goes all the way up to RP. If you have a hit, good, done. And if you don't, go and see if it's in L2R. If it does, go all the way through CEO pipeline, submit the IO, and then go all the way back and wait for the read to finish. That's what it does. And the IO comes back. On the interrupt context, you click the task queue. Task queue finish the CEO pipeline, wakes up the thread which is waiting on IO, right? So at least for L2R, we don't really have to go to CEO pipeline, assuming that your device is faster and you get a response within maybe 100, 200 microseconds, right? So that's exactly what we did. Essentially, short circuit the whole pipeline stage to do a blocking read here on behalf of the application thread, and do essentially what we do typically for L2R done case, including filling up the debug, and essentially wake up the application thread. So with this, we could double the IOPS. It went up to 200K. Then we hit another issue where today with L1 arc, when it gets filled up, it blocks the application thread. We sleep for a while, wait for it to evict to a stage where it, to a certain threshold, then make. So it causes your IO pattern to just go up to a level, pause for a prop down. So it gives you a typical sawtooth pattern, right? So with L2 arc, it does not solve that problem, because even when you have data coming from L2 arc, you fill up arc with that, L1 arc with that, right? Getting into the same bottleneck. So we changed the semantics of what exactly L2 arc means. So this is typically what L1 and L2 arc does today. So you could have buffers, in this example D2 and D4, which could be both in L1 arc as well as L2, which this is what is causing you to cause the cache throttling. You fill up the arc, then you wait for it to shrink, right? Where you could have just put it only in one case, in this case in L2R, and read directly from there. So essentially implementing the arc as a extension of L1 arc rather than just having duplicates on both sides. So you have buffers either in L1 arc or L2 arc, not both. So which avoids you filling up the L1 arc, thus causing the thrashing. So with that, we could sustain the IOPS at same rate. So this is not a specific to CFS thing, but just wanted to bring it up. I mean, the next thing is what we can do with more than one device, right? So with one device, we could get 200 IOPS, but we couldn't go beyond that because the older versions of kernel doesn't balance the IRQs across all the CPUs. I think I'll skip that part. I think this is something we need to take it up further, what we can do beyond that, but it's not something that's a priority for us, at least for now. So the summary is that we could get 1 million IOPS with 3 VMs running CFS with 16 pools. So I have something that I can demo.
Did you do this all today?
Not really. So it's I don't want to say it as the hackathon project. Just
you should come back next year and give a talk.
Yeah, I will definitely. So yeah, so it's a running FIO test which with 256 threads on 3 devices doing around 300 IOPS, and so this is the L2 arc. So arc stats, right? So your L1 arc is set at 32 gig and stays there, and that's what we want to do, right? And all your data is coming from L2 arc. So in this case, the whole data set or the active data set is cached in L2 arc. That's pretty much it.
Hello everyone. My name is Gaurav from Nutanix, and today I wanted to talk about how ZFS handles a thinly provisioned disk. It's a thinly provisioned disk. I don't care how much storage I have in the back, but what happens if you give a 1 petabyte disk to and try to create a pool? So how much memory do you need really to import that kind of a pool? So I mean, one would take that, okay, you need to initialize the meta slabs and, all that what it takes. But, ZFS already partitions the disk into 200 meta slabs, right? Now, the problem with that is you get a meta slab size of 8 terabyte, and then it basically defeats the purpose of having partitions in the first place because you have to load that much of, free extension memory. So, we can restrict the size of the meta slab size as maybe, let's say, I pick up a number 64 GB. But even with that, we're going to have around 16,000 meta slabs on a petabyte disk. And each MSP structure, when you initialize, and in addition to the range trees that we initialize in the initialization phase, it takes around 10 kilobytes of memory. So with 16 K of meta slabs, it's around 160 meg of memory that we need, right? So what's the big deal? Let's throw some couple of extra megs. But here's my setup, and that's the problem that I have. That I have a pool which has a lot of disks, and they're all thinly provisioned disks. I don't want to, care about what size the disk is. And it's just not one single pool, but I have multiple pools because hey, I want to load balance. I want to move around these pools from one volume group, from one VM to another VM. So looking at this configuration, I need around 20 gig of memory just to import the pools on a particular VM. And we have seen cases when we actually started with this kind of a configuration, we couldn't even import on a 12 gig system. So how do we solve this problem? So I started looking into this as part of this, where all this memory is going, right? So if you look at the MSP structure, the structure itself is 2 kilobytes. And then during the MetaSlab in it, we also create some range trees. Each range tree is 624 bytes. And for each MetaSlab, we end up allocating, bunch of these range trees. And if you do the map, the total will come out to be around 10 kilobytes. So this is on 0.8 master, the master branch. What we are using internally is 0.7, which I think is even less than this. I mean, it's around 8 kilobytes or something. But yeah, on the master, it's around 10 kilobytes per MetaSlab. So I thought maybe, what we can do is we don't need all these structures at the time when, we are importing the pool. We don't even need those structures because unless we do some allocation on that. So all the range we still need some basic data structures so that we can look at the MSID, for example, what the fragmentation level is, pick up a MetaSlab based on the weight and all those things. So we need some bare minimum data structures. But we don't need to create all this, free tree and the alloc tree and all those things because we are not doing allocations yet. So can we divide this structure into two parts, a static one and a dynamic one, which is only upon preload. Obviously, you don't want to incur the cost of allocating these structures when you're actually allocating blocks. So you need to, do it in the background somewhere, like during the preload is a good time. So how much do we save from this? The previous structure I showed, it only is like around 368 bytes, the static one. And then if I take the worst case example that I took, where I needed 20 gig of memory to import the pools, I only need like 700 meg now to import those pools. So I did some prototyping on this. I think the font is bad, sorry about that. So at least what I could achieve is I could create a pool of a single disk, and I could see that so I created a different KMM cache for allocating this additional data structure, the dynamic one, and I use system tab to make sure that I'm only allocating 3 times because the 3 is a preloaded number of MetaSlabs. So I'm not allocating it for all the MetaSlabs. Although I can't explain why when I look at the slab output, I have 74 objects in it. So I can't explain that right now, but I'm just still working out on ironing some of these details as to where these objects are being created. But yeah, in a nutshell, that it should definitely save a lot of space unnecessarily, and it's already thinly provisioned. So I should not be worried about whether the disk is large or small, because I understand that ZFS when started, we had all those physical drives which are limited in capacity. But if you're running on VM solution, then it could be any size disk, and ZFS should be able to handle it. That's all.
Okay, so I'm John Gallagher. I work for Delphix. And a little while ago, I added some code to ZOL, which allows you to wait synchronously for certain pool-wide operations that are otherwise asynchronous, like scrubs, device initialization, replacing a device, things like that. And an operation which falls into that category, another operation which falls into that category is trim, but I didn't add that when I upstreamed it, so I thought this would be a good time to go back and add that sort of missing feature. So what that looks like is I can do do a trim, zpool trim. I got -R to make it a little bit slower so we can see it, and then this is a -W flag that I added, which means instead of returning immediately after kicking off the trim, wait until the trim is finished, or until we're not trimming anymore, until it's finished or it's canceled or the pool is exported or something like that. So we can kick that off, and look at the status. You can see it's trimming, but the command has blocked. And it's not going to return until we cancel the trim or it finishes. And in case you didn't kick off the trim initially with the -w flag, but you do want to wait for it, there's also this zpool wait command. So we do a zpool wait, say what we want to wait for. In this case, trim the pool, and it will block until the trim is finished. And if you want, you can also get periodic updates about how much it has left to trim. And then I'm not going to wait for it to finish, but I will cancel it. And both of these commands that are waiting should return immediately when we cancel the trim, and they do. So that's it.
Okay. So one of the requirements that we had internally was given 2 snapshots, report what blocks have changed for a given file. So if you have a file which is present in 2 snapshots, you want to see which blocks of that file have changed. So that was the requirement, and we're trying to figure out what to use. And I was walking through the DMU diff code path, which essentially does that, and there's this Travis BP. So found that there's already a function which does this, which is Travis dnode. So we hooked into that one, and what we essentially do is figure out what's the TXTs of the 2 snapshots. So if you have snapshot S1 and S2 in those chronological order, so you basically figure out which is the TXT of S1, and then you basically want to report all the blocks of that dnode which are born after the TXT of S1. So that's pretty much already built in. So I was trying to use something that was there in ZDB and use that to report, but then figured that we already have Traverse dnode, which essentially does that. So all it needed was a little bit of hooking up. I still don't have the plumbing done, which can pump it back into the user land, but it right now reports it in dmessage or CMN error right now. Just reports in there. So that's the, let's see if I can. So, I mean, slightly wacky interface in there where B is report the block diff, and the inode or the dnode that we are talking about is 5. And see these in here, which are reporting the blocks. It's still ugly because I'm just using the SN block printf macro in there, but it's essentially reporting the blocks which have changed in there. But so now I need to hook it back into the pipe that we set up for ZFS diff, and then report it back in. So that's what we have there. Oh, I'm sorry. I'm Sanjeev. Work for Nutanix. Thank you.
So I saw the decidedly unglamorous but kind of exciting project of cleaning up the ZFS and the zpool command man page, which, as I can see, is a thorn in your sides as well as in mine. And so I took the approach of breaking out all of the subcommands into their own man pages. And also reorganizing, and this is really just a spitball take on it, but reorganizing into topics, the subcommands, because they were fairly arbitrarily ordered in there. So the ZFS command man page currently looks a little bit like the Git man page, where there's all of the subcommands listed in separate topics. I left the long examples section at the end, thought about pulling it out, wasn't sure if that was too much to change. But I did pull out a lot of the overview information into a ZFS concepts man page. And all of this, I think, is subject to editing. And just to give an example of what one of the command man pages looks like, bring in the synopsis just for those commands, and then copy verbatim the description section that used to live in the top level man page. The one that was a real relief for me to get done was the ZFS properties, which it needs a little more boilerplate at the top, but now it's in its own file. And so you still have to scroll forever and ever to get to the bottom of all the properties, but they're at least in their own file. One of the great things about this is that as more distributions are merging into OpenZFS, it'll make the changes to the topics more atomic, and also some of the platform-specific stuff that's not in this repository right now, like FreeBSD jails, should be easier to work in via preprocessor rules or something of the kind. So that's what I got done today.
Open the pull request.
You want to introduce yourself?
Yes, I'm Ross Williams. I don't currently work for anyone, but I'm looking to change that.
Okay, I'm Paul Zakowski. I was looking for something to work on, and I wasn't feeling super inspired, so I just picked an issue off the GitHub ZFS on Linux issues section. And someone had reported that when native encryption is enabled, sync with writes are slow. And you can see the link there if anybody's curious. It's been there a few weeks. The test results that were posted by the user. And what really kind of catches your eye is they were only getting, the DD command was only getting 117 megabytes per second when using sync semantics with encryption. And you can see the delta when you're asynchronous wasn't too bad, and there's quite a pronounced delta when you are using sync. So that kind of caught my eye and thought it beared investigation. This is the pool that the user created for the reproducer. It's got a single disk VDEV and a single log VDEV. A file VDEV, I mean, they're both file backed. And the test is to run this DD command. They actually had a higher count, but I didn't have enough memory to do this on my laptop. So I'm a little concerned about the block size equals 10 meg too. I'm not so sure if that's might be related to everything that's happening. So to troubleshoot this, I created a reproducer script based on the ones that were there, and I confirmed the issue. It wasn't as slow for me as it was for that person, but it was still different and not as good. And then I really wanted to do a flame graph because it seemed like the cool thing from yesterday and the day before, but I couldn't get that installed. But I have perf tools, so I figured I'd use that. I was suspicious about the setting of log bias equals latency. So what I decided to do is use perf count, func count from perf tools to count the number of times that we called ZIO encrypt with the different settings, whether it was log bias of latency or throughput. And these are the results that I got. With log bias equals latency, where it's going to hammer that log device, there were around 6,000. I just ran it twice. Calls to ZIO encrypt. When you had log bias equals throughput, they were in the 4,000 range. So some low 30% fewer calls to ZIO encrypt. I don't think that's conclusive, that that's exactly the root cause. I wasn't able to get to the exact root cause today with the time I had. But I think it's safe to say that it probably wasn't helpful to have that many calls, because you're basically calling it almost twice for every block you were putting through. And I've gone ahead and updated that issue with what I found out today. So that's all I got.
So I really don't have much. I'm Tim Chase. I don't have much of anything to demo, even though I've got my laptop connected. I worked on two unrelated things today. One for end users and one geared toward developers. The first is I wanted to refresh a patch set that I made some time ago to deal with on-disk corruption, particularly corrupted block pointers, which seem to be a frighteningly common occurrence in the real world. And the reason is because I don't know why they're common, but they just seem to be. So what this patch set does is it adds, I call it hardening. It hardens the entire ARC read path and some other areas. My goal today was to get it ready for a pull request, which I think I've done. And that led into part 2 of the thing why I don't have a demo. Because everything needs to be able to be tested nowadays. And I'm thinking, well, how can I test this thing? And after chatting with Brian a little bit, I thought the suggestion was made to use the Z-inject infrastructure. Unfortunately, the whole Z-inject infrastructure doesn't really give what we want for this type of testing. Because what I really want to be able to do is I want to be able to test a pool that actually has valid checksums but invalid data in its metadata. And that's just not something that the Z-inject infrastructure is prepared to do right now, at least not for data in D nodes, which is where the block pointers are kept. So I'm going to post this as a pull request shortly without any test infrastructure in place right now, which means that I will probably follow on with some work on the Z-inject infrastructure to be able to produce something that allows it to actually be tested. The second thing I worked on, I actually have a demo for, and it's going to take about 2 seconds or so, geared toward developers, and this was just one of these, it looked like it would be a cool thing to do projects some time ago. And that is, under Linux at least, we've got a proc file called TXGs, and what it does is it shows information about transaction groups. And I occasionally read about the sync to convergence thing, and it's like, okay, be interesting to see how many sync passes each transaction group takes. So what this patch does, it's pretty simple. It adds a new column called passes, and that shows how many sync passes were required to make that transaction group get flushed out. And I did this a while ago, and I was kind of sitting on it, and I figured, well, if I get this kind of positive reaction here from developers, I'll put it out as a pull request. And of course, now I have to wonder to myself, how does this fit into FreeBSD and other OSs that don't generally use a proc file system, or what the equivalent there is? But in any case, those are my 2 things I worked on today.
Who else would like to demo something? Or tell us how you worked on?
Hi, my name is Paul Danielink. I spent part of today rewatching my talk from yesterday to critique myself. It turns out I say a lot. That's the thing I noticed. The other thing that I did today was was going to try to get a Rust file like building as part of the ZFS kernel module. That was like my aspirational goal. It turns out that that was an extremely aspirational goal because I couldn't even get like an open source. I just like pulled a GitHub repository where people created a Linux kernel module in Rust, and I could not get that to compile. Like I followed exactly the steps they gave me, and it spewed out inscrutable compiler errors. So I spent the last hour and a half tracking down like, oh, it turns out that the arguments are being like passed slightly wrong to Clang, and like I've learned a lot about compiler arguments that I didn't want to know about. So that is the extent of my progress today.
So what we're going to do next, if nobody else is interested, I'm going to post a survey to the Slack channel, and you'll all have about 100 seconds to get on there and vote, because I don't want to keep everybody sitting here forever. All right. You can see it now, right? All right, so The results: in first place with 21% of the votes, Metaslab Worst Fit Allocator, Don Brady. Where are you, Don? Come on up and choose your prize. So you have the choice of a tri-bit, it has 3 bits, Bluetooth speaker, or a RAV power wireless charging thing for your phone for your day. All right, awesome. I think we have a tie for second place. All right, in a tie for second place, Sarah with the SDB B-Tree Walker and Ross with the man page cleanup. Come on up, and I think there's enough that we have plenty of choices, so you can each have your choice of places. We tested them with with iPhones, and I know they've also worked with Android.
Oh.
It's pretty cool, actually.
Yeah.
I think I'm gonna have to buy one for myself after this. I know. Okay, well, we have plenty of prizes, so I'm gonna go so there's a tie for second. I guess this is fourth. I'm gonna do fourth and fifth. I don't even know who they are yet because I haven't moused over them. But those are the ones that like the numbers on here. So in fourth place, the SDB mutex command, Seraphim and Jordan. These are the chargers and the speakers.
You said it if you want first.
Yeah, we have plenty. So.
Okay.
And fifth, Saji with L2ARC performance on NVMe SSDs. Awesome. I really do like your talk. You should come back and give a full talk next year about it. So this is the charger and this is the speaker. Cool. All right. Do we have any logistic notes?
Nothing other than kind of clean up around you and maybe help pull some chairs back.
Yeah, clean up, and I think the event ends at 5 o'clock. So.
Yeah, you have time to clean up.
We're amazingly 10 minutes early, which I don't think has ever happened.
That is
In the
amazing.
history of this.
Yeah.
You were all so great at giving concise talks about your hackathon projects. So thank you very much. Join us a week from today on the call if you'd like to hear the talk that had to be canceled from yesterday about securing the cloud using OpenZFS, and also status updates on projects in progress, and we'll have that call every month. And then please join us again next year. We'll announce the next year's conference dates in a few months.
And Michael and I added a few links to the leadership team meeting on the website.
Good. So you'll have an
You can
easier time
actually
finding
find
it. Yes. I also post those links on Twitter and on the developer at OpenZFS mailing list, which I would encourage you all to join. Thank you.
Thanks, everyone.